we'll start the session at 6:10. If we'll wait if some other people are joining. Okay. Meanwhile, if you have any questions from or any doubts from last week, you can ask me now, or else you can put in chat also if it is fine. Yeah, regarding that question, last time I have also put it in the. Let me check. Yeah, in this I have put. Yeah. So here in the biosphere water, what we were referring to was the water which are stored inside the living organisms. So if you consider that, in case of that, then it is like nearly 0.0004% of the Earth's terrestrial surface water. So in that case, as I wrote here, and this work I have also shared in the folder if there is something. So there you can check. So you can see here for atmosphere. Uh, yeah, you can talk if you want. Understood, right? Okay. Okay, fine. Meanwhile, if you guys have any other questions or any doubts from last week, you can ask me now. Maybe at 6:10. What is it? Yeah, so maybe we can start the session. Okay, good evening everyone. So today we are going to discuss about the week 2 lectures of the course Groundwater Engineering. Hello, I am Balram Shah. I am the PMRF TA for this course. I am a PhD scholar at Interdisciplinary Center for Water Research at IISc Bangalore. And today we'll be discussing about some of the uh, questions which you can which will help you to answer the assignment questions for this week's. And if you have any questions for or any doubts regarding this week lectures, you can ask me. Okay, maybe I'll switch off the audio because last week there was some bandwidth issue. Maybe I will keep on keeping on. I'll keep turning on video whenever required. Okay. Okay, fine. Okay. So in this week lectures, before going to that, in the last week at the end or in this week only, we had a question that is the plants adaptable to live in an environment with abundant liquid water are. So you can put your answers in your chat box or you can speak. Okay. So last week also we have discussed, and this week also, if you just know what is the question here, that the plants which are adaptable to live in an environment with abundant liquid. What do you think the answer will be? A. Okay. Anyone else? Anamika. Okay. So here, what is the question? The question is abundant liquid. Abundant liquid as in where okay, B, where enough amount of water is there. So xerophytic plants, as Hani said, xerophytic plants are the plants which are adaptable to survive in an environment with little liquid water. So last week also I discussed that when it is like when desert environment and all are there, if we have to reduce the desertification propagation, then what we do, we put xerophytic plants because those are the plants which need less water. Whereas here the question was that with abundant liquid water. So hydrophytic plants are the plants which live in water, okay, and which adjust to their surroundings. So the correct answer for this will be B, that is hydrophytic plants. Okay. Okay. So before going to the other questions, let us discuss first. First lecture of this week was related to the surface water versus groundwater. So see, we know that what is surface water? Surface water is the water that is available on land in the form of, it can be in any form. It can be in the form of rivers, oceans, seas, lakes, or something like that. Correct. Rivers, lakes, something like that. Whereas, what is groundwater? Groundwater is the water that occurs below the earth's surface, right? So, when it is below the earth's surface, it occupies all or part of the void spaces. So, if we write here, so it occupies all or part of the void spaces. Many places you will see that void spaces is written in terms of interstices. So that is also used in complementary. Okay, yeah. So groundwater, so this occurs where it occupies all or part of the void spaces in the soils or geological strata. Yeah. So it occupies all or part of the void spaces in soils or geological state. So why I am calling here all or part? The part is because all the rocks are not fully saturated. So, or let's say the voids in these soils or rock layers are not always filled with water. It is only possible when the voids are interconnected. So let's say you have voids in the soil. However, these voids are not interconnected. So it might be possible that their water is there, but it is not reaching to other voids. So that's why groundwater occurs or it occupies all or part of the void spaces in soils or the geological strata. And we also know that groundwater we also called as subsurface water, right? Okay. And the surface water we know can be used in drinking, public uses, irrigation, thermoelectric power industry to cool, let's say, electricity generating equipment, thermal power plant, and so on. So surface water has been extensively used. Whereas if you see the groundwater, it also serves almost the same purpose. However, uh, there has been one, yeah. and there had been several aspects where we use the groundwater. Now you will see two terms, that is shallow water table and groundwater table. Sorry, deep water table. Okay, so shallow water table, if you are here, we consider the reference as ground surface. So if the water table is close to the ground surface, we call that as shallow water table. Whereas if the water table is far from the ground surface, we call that as deep water table. And many places you will see that it is written as closer to MSL or something like that. What is MSL? MSL is mean sea level. Okay, and we also have read about water table, right? Water table, or let's say if, okay, water table is done. Now we'll move to the water level, or many places it is written as GWL. What is GWL? GWL is groundwater level. Okay, and this is also measured from ground surface. Okay, maybe let's say there are so many dug wells and so bore wells and so on, where generally, let's say if you see the Central Water Commission of India and all, they take this groundwater level data from so many wells. So in India, if you see, there are more than 20,000 or more than 30,000 number of wells in which CWC, or let's say state, has their authority to take the groundwater level data. Okay, and generally the units that you will see is written in MBGL. What is this? M denotes meter and BGL denotes below groundwater, below ground level. Okay, so from the ground surface, or let's say if there is some surface here, ground surface, then wherever the water level is, let's say this is the water level, so it is generally taken in this way, and that's why we say it as below ground level. So this much meter below ground level. Okay, I hope how ground level units and all are clear. Okay, so now if you see the difference between surface water or groundwater, not difference, let's say if you see all the characteristics, then you will see that in terms of temperature, surface water will vary with season, whereas groundwater will almost, it has a relatively constant temperature throughout the year, or maybe throughout a decade, if you see, unless until there is any external heat source or something like that into the groundwater. Then the turbidity or the suspended solid. This SS is suspended solids. Okay, so the turbidity or suspended solids level in the surface water case, levels generally varies there, because let's say if, what is turbidity? Turbidity is the characteristics of water in which, let's say if you shoot one light through it, it should pass. So if it is passing, then it is low turbid, and if it not passing much, it is high turbid water. Okay, and suspended solids, so these are kind of impurities, you can see. So if in the surface water it is more polluted, the turbidity will be more, so that's why it can be possible that in surface water the turbidity is sometimes high, whereas in groundwater it is low or nil except in the karst soil. Okay, coming to the color and other characteristics, if you see, we have seen this in the lectures. I will not go much detail into it. Maybe something which we need is color. You will see that because of clays or algae, there is colors, and let's say for humic acids in surface water there will be color. However, in groundwater mostly it will be colorless. Sometimes due to dissolved solid there will be some color into it. Okay, if you see nitrates, it is relatively generally low levels. Sometimes it is high. Okay, so yeah, so these are just the information. You can just go through it and we can have the information. Any question you have here? If not, we'll move to the next part. Okay. Okay, so the question we have is industries like power generation plants and chemical refineries often prefer dash because its temperature is dash. Can you guys give me answer for this? Anything that you can think of? So industries like power generation plants or chemical refineries often prefer first option we have surface water or groundwater, because it is A and B are surface water and groundwater, again C and D are groundwater, because its temperature either remains steady or varies with season. So we know that for groundwater the temperature generally remains steady, right? Or you can say relatively constant, right? So because of these characteristics, the industries like power generation plants or chemical refineries, where let's say if the temperature varies, then what will happen? They have to keep one other instrument or equipment so that it can have a constant temperature, so that they can use that water again for the next purposes. Whereas from groundwater, they are directly getting this kind of properties, and hence they will mostly use groundwater for their work. Okay, so industries like power generation plants and chemical refineries often use groundwater because its temperature remains steady, and therefore the answer will be option B. Okay, okay. We'll move to the next question. The next question is, water table is generally dash in uplands and dash in the valley bottoms. Anyone have any answer for this? So generally, what will happen in uplands, or let's say where uplands, as in let's say hilly areas where topography is high, okay, and in valley bottoms, what will be the topography? It will be mostly plains, right? So we know that in areas like mountains, hills, or somewhere, the water table will generally be deeper, whereas in plains it will be very shallower, and hence the correct answer for this will be in uplands it will be deeper, whereas in valley bottoms it will be shallower. Okay, okay, so the correct answer is D here. Okay, the next question, this is just an information question, maybe you might not know also, that is fine. So the question is, the most abundant natural acid in water cycle is, anyone wants to give a guess on this? A, okay, anyone else? Yeah, nitric acid is not the correct answer. Mostly, if you see the natural acid that is available in water cycle in significant amount, is the carbonic acid. Okay, which can make the water maybe little hard or something. Okay, we'll move to the next question. That is, hard water contains large amount of dash. So generally, if you see the hardness of water, do you guys know why or what is the reason behind the hardness of water, or which, let's say, elements, if you can say, or compounds? A, okay. Uh, no, lead won't make it hard. So if you see the hardness of water, it is generally because of the dissolved calcium and magnesium salts. Okay, so therefore, if you see the let's say which ions and all are there, then you will find either calcium is there or bicarbonate, that is CO3 2 minus will be there. Sorry, calcium bicarbonate will be there. Wait a minute. Sorry. Yeah. Hmm. So calcium bicarbonate. So in the form of calcium bicarbonate or magnesium bicarbonate or calcium sulfate or magnesium sulfate in the form of either cal bicarbonates or sulfates, it will be there. Okay, so for this, what will be the answer? Can you tell me? C, that is calcium. Okay, fine. The correct answer will be C for this. The next question which we have is what percentage of groundwater wells in India showing decreasing water table? Okay, just to note that in the percentage here shown is old value. It might be possible that after 10 years or something, the value might change. Okay, so for now, the option that we have is 44%, 54%, 64%, or 74%. Anyone? It's just information thing. So the correct answer for this will be 54%. So around 54% of the groundwater wells in India are showing decreasing water table. Okay. Okay. So the next question is what it is not available for evaporation from. Yeah. So after this, there is one question. I want you guys to have some pen or paper with you so that you can solve. There will be a one small problem question from this. Okay. Now coming to the question, what we have is water is not available for evaporation from. So we know evaporation last time, right? We have studied about water cycle. In water cycle, we have the major components are precipitation, evapotranspiration, then runoff, or the change in storage, right? One of them is evaporation. And remember, what is the difference between evaporation and evapotranspiration? Evaporation is the amount of water which is coming from the ground or let's say our atmosphere. So in that it is from open water, okay, open water or land or something like that. But if it is coming from vegetation, we call that as transpiration. And that's why over land, whatever water it is coming out in the terms of water vapor, we call that as evapotranspiration. Okay. Okay. So now the question is, water is not available for evaporation from. Option C, right? Anyone else? Yeah, so let's say if we make a schematic, let's say this is the groundwater surface or ground surface, okay, and somewhere here we have water table, and if you remember that above water table there will be one layer which will be due to capillary rise, right? It will be a capillary fringe. And if you see before that, this zone is called the zone of aeration. Whereas there will be, let's say, if we consider one impermeable strata, this we call as saturation zone or zone of saturation, right? Yeah. So there will be some water here in the form of soil water or soil moisture, right? There will be one intermediate zone, so on, right? So yeah, so this one we know is the water table, and we'll have, let's say, some vegetation. This is vegetation, let's say. Okay, so from surface there will be evaporation, right? Yeah, so here the transpiration that is happening, we are calling that also as evaporation for now here in this question. So from vegetation also there will be some evaporation. From open water surface it will be there, right? From vegetation it will be there. From ground surface also it will be there because there are soil water into it. So these soil water will also evaporate. So the correct answer in which the water is not available is water table. So before the water table, mostly the water can evaporate. After water table, generally it does not. Okay, so the correct answer is C. Okay. Water balance equation uses the principle of, okay, so for this, first I'll explain a little. Okay, so while studying the water cycle, we have studied about the components of water cycle, right? Precipitation, evapotranspiration, runoff, or let's say infiltration, percolation, then groundwater flow, storage change, and so on. However, let's say if you see the water balance equation or water budget equation, how you can write it? Let's say if you consider system first, okay, you can consider any system, okay. So in any system, we know that if some amount of mass is going, so let's say if there is some inflow and there is some outflow, then whatever remaining will be there, that will be the storage in the system, right? You can consider the whole thing as a system, or you can consider a small part as a system. It depends on how you are seeing the system, right? Okay. So in case of water budget or water balance, what we are doing here is we are applying the conservation of mass, that is whatever mass going in and coming out will be equal to some change in storage. Okay, so if outflow is more than that of inflow, then what will be there? The change in storage will be in positive or negative. If outflow is more than inflow, then the change in storage will be positive or negative. It will be negative, right? This water budget or water balance, whatever you say, here we call this as water budget equation or water balance equation. So here, in case of water budget, how you will write the major components if we consider. So let's say, so conservation of mass here, what it is doing, it is nothing but the continuity equation, right? Okay. So let's say if there is a system for, let's say in water we are considering, let's say this is a basin, which is a system. Okay. Now there will be precipitation, which will be the inflow. What else? What all output will be there? We know that evapotranspiration will be the output, major components. R will be the runoff, and there will be some storage change, that is S. Okay. Now let's say it is an system in which there is some inflow from other basin also. Okay. So let's say maybe Q surface water, and then in groundwater also, if you consider, let's say this as some basin like that, there is some inflow from other groundwater also, other basin. Okay, so if we see all this, we can write it in the form of P plus Q, let's say surface water inflow, plus Q. Q here is the stream flow, okay, or the water that is coming. So here SW is the surface water, GW is the groundwater. Okay, and what all outflow we have? We have evapotranspiration. Let's say if some surface water is going out, okay, so let's say we write it as QSO. So QSO minus QCWO will be equal to plus minus, or here let's say if it is whatever change is there, plus minus storage change, plus minus some error term. Okay, so if you just write it in one line, then you can write it as QSY plus QGWI minus E minus QSO minus del S plus minus N. So here, if you consider one error term as plus minus, then you can write it as minus also, equals to 0. So this is what our water budget equation is. Okay, so here this n can have a decreasing term which accounts for, let's say, error estimation. Okay, yeah. Okay, so we'll move to the question then. The question we have is water balance equation uses the principle of. Your options are conservation of energy, conservation of mass, conservation of momentum, or none of the above. Anyone? Okay. So as we have discussed that it uses the principle of conservation of mass. So if you see the major component, it should be P minus Et minus Q or R, whatever you say, equals to the change in storage. Okay, or you can write it as dsdt also if you see that basin in which we have drawn S here. See here we have written S, right? So we can write this as dsdt also. Okay, so this is applicable where we have closed system. We can have some open systems also. What is open system? Open system is, let's say, if there is some inflow or outflow which is out of the system. Let's say if some surface water is contributing from a different basin, we call that as open system. Okay, and so what we are considering here, we are considering only precipitation is the only input source. If let's say you are coming from some other basin and putting water from other basin, it won't be a closed basin. Okay, so the correct answer for this will be conservation of mass. So correct answer is B. Okay. Okay. So where do we use this water balance equation? Mostly it is being used in all the aspects of, let's say, uh, management of the water supply, or let's say if you want to predict whether there will be water shortages in the coming months, or let's say in the 1 year, you can use the water balance approach. So it is mostly used in groundwater hydrology, surface water hydrology, let's say irrigation, runoff assessment. For flood control also it is used, for pollution control also this conservation of mass can be used. Okay, and yeah, so it is also, let's say if we know how much water is where, so if we can estimate each component, so we can also design the subsurface drainage system, which may be, it can be horizontal, let's say pipe flow, so it can be pipe flow. So mostly this pipe flow part, the designing part, if you study any fluid mechanics subject, you will study there, like how the pipe flow will be there, how it is designed, and so on. And it can also be vertical drainage systems, let's say drainage by wells and so on. Okay. Okay. So we'll move to the next question. Any questions till now? Okay, we'll move to the next question. Okay, so the next question is, with respect to the Earth's land surface, which of the following expressions is correct? This one is a simple question. So here we are considering long term. So we are considering for a very long term, let's say 100 years. Okay, so let's say for 100 years, we consider that whatever the storage change is there, that we are considering as negligible. Okay, so based on this, can you answer this? What will be the answer for this? So can anyone guess what will be the answer for this? So what we have said that for long term, let's say for 100 years or something, we are considering that the change in the total water storage is zero. And based on that, can you answer the question? Any guesses if not? Okay, so just now we have seen that inflow minus outflow should be equals to change in storage, right? Plus minus del S, or change in storage. Here we am saying that this del S is zero. So what is the inflow? Inflow is the precipitation, right? And what are the outflow? Outflow are evapotranspiration and runoff, right? It is equals to zero. If we write in the form of P, we can write it as E plus Q, right? Q is the runoff and E is the evapotranspiration. Okay, so the correct answer will be C, that is precipitation equals evapotranspiration plus runoff. So the correct answer is C. Okay. Okay, so the next question is a small problem which you need to solve. So the question is, a lake had a water surface elevation of 103.2 meter above the datum. So this, let's say, consider this datum as any reference, okay, at the beginning of a certain month. So let's consider any month, let's say January month. In that, in the beginning, the water surface of a lake was around 103.2 meter. Now in that month, the lake received an average inflow of 6 meter cube per second, 6 meter cube per second, and from, let's say, from surface runoff sources. And in the same period, the outflow from the lake had an average value of 6.5 meter cube per second. Now further, so what all we have, let's say water surface elevation of the lake. Let's say if I write T, or maybe 1 and 2 I'll write, okay. 1 I'll write for the beginning, okay. So it is 103.2 meter above the datum or above reference, okay. Now in that month, the lake received an inflow of 6 meter cube per second, and in the same period there was an outflow of 6.5 meter cube per second, okay. Now further, in that month the lake received a rainfall of 145 millimeter, and evapotranspiration or evaporation from the lake surface was estimated at around 6.10 centimeter, okay. Just keep note of units. So we have to calculate the water surface elevation of the lake at the end of the month. So we have to know what is WSE2, right? Also, it is given that the average lake surface area can be taken as surface area A equals to 5000 hectare area, okay. And just to note that 1 hectare area is, sorry, 1 hectare area is 1000 kilometers square. 100 kilometers square. Okay, and we are assuming that there is no contribution to and from groundwater storage, so those are zero. Can you calculate and tell me how much you are getting? Maybe I'll give you guys 5 minutes to work on this problem. You do this and then let me know how much you are getting, okay, and then we'll see. So this one, just to note that 1 hectare area is around 10,000 meters square, not kilometers square, okay. Yeah, sorry. I'll give you guys 5 minutes. You guys do it and then let me know how much you're getting. If you have any question in between, you ask me there. Okay, if you're getting stuck somewhere. I'll start solving also, and then you guys can also do. Okay. So firstly, let's say we consider the time interval of the month as del t, for example. Okay. So now if I ask you, like, let's say write the water budget equation for the given problem for the lake, how will it be? It will be simple, right? It will be input volume minus output volume will be equals to the change in storage, or we should say change in storage of the lake here, right? Now if we write this input volume, what all we have, you see here, sorry, we have a inflow, right? Average inflow, we have the lake received an average inflow of 6 meter cube per second from surface runoff sources, and in the same period outflow from the lake had an average value of 6.5 meter cube per second. So we can write it as input volume will be, let's say if I consider inflow as I, then I into del T will be the volume, right? Because what is I? I is in, let's say, in the unit of discharge, that is meter cube per second. The total volume will be, how we will get the volume from discharge? You just need to multiply from the by the time that we have. Here we have considered del T as the time interval of the month. Plus, what other input source we have? We have precipitation, right? But now the precipitation is for the whole lake. However, we have this precipitation is in which unit? It is in millimeter unit or depth unit, right? And here we are talking about volume. So how we will calculate the precipitation over the whole area or over the whole lake? We'll just multiply with the area A. Okay. So this is the input volume minus what will be the output volume? Let's say if we consider output as O, and then change in or the time interval as del T, and any other output we have the evapotranspiration or evaporation from the lake. Okay, not the evapotranspiration. So E, let's say if is the evaporation, then evaporation again is in depth unit. So we have to convert it into volumetric unit. So what we will do, we will multiply it with the area of the lake, that is A. Okay. So now we have input volume, we have output volume. If we write the change in storage of the lake, how much was it? So for now I'll just keep it as delta S. Now you just need to put all these things from the problem, and then we will get how much water surface elevation is there at the end of the month. Okay, till this it is clear. Are you guys going in this direction or anything else you guys are doing? So you can do in any of the unit. So here we are talking about input in the volumetric unit. You can go into depth unit also. Okay, just note that you should be consistent with the units. Okay, okay, I'll calculate the input now. So let's say the time interval del T for month was how much? Let's say I'll write in the top. That is how much we have. For now, let's consider 30 days are there. 30 days into 24 hours into 60 minutes into 60 seconds. How much it is? Let me calculate 1 minute. Yeah. So it is around 2.592 into 10 to the power 6 seconds. Okay. Okay. So we have delta T now. Sorry. Okay. Now we have delta T, right? What else we have? We have the inflow volume IS. Average was how much? 6 meter cube per second, right? So if we calculate I del T, then it will be 6 was in meter cube per second, right? And 6 into 2.592 into 10 to the power 6. That is in, this one will come in meter cube. Okay, how much it is? 2.592 into 6. It is around 15.552 into 10 to the power 6 meter cube. Okay, that means how much? 15.552 million meter cube. Okay, similarly, if you calculate the outflow volume, we have 6.5 into 2.592 into 10 to the power 6. That is equals to 6.5 into 16.848 million meter cube. Okay, and P into F, if you do, how much it is? Precipitation was how much? 145 millimeter. So I'll come calculate in meter. Okay, 1000 divide into how much was the area? 5000 hectares into 10 power 4 meter square. This is how much? 145. So it is coming around 7.25 million meter cube. Okay, I'm converting all into million meter cube. And similarly, E into A, vapor transpiration was how much? 6.10 centimeter. Okay, 61. 100,000 into again the area 20/4 will get around 3.05 million meter cube. Okay, so now we have all the accounts. So if we calculate del S, how much will be the del S? I into delta T is 15.52552 plus PA is 7.25 minus 16.848 plus 3.05. Can you calculate this and tell me how much you are getting? Okay, I am getting somewhere near 2.904 million meter cube. Okay, but now we know that how much storage change has happened in that month. But the question was to calculate the water surface elevation that will be there in at the end of the month. So how much will be the depth? So this we are considering that whatever storage change happened in the lake, that is, and that will reduce the surface elevation. Okay, so if we just divide this storage change by the area, we'll get how much surface change or the water surface elevation change has happened. Okay, so here del Z, we are saying what is del Z? Del Z is the change in water surface elevation. Okay, okay. So how much we have? 2.904 into 10 to the power 4, so 10 to the 6 divided by area is how much? 5000 into 10 to the power 4 meter square, right? How much we are getting? I'm getting somewhere near 0.058 meter. So this is the change in storage. Okay, and what was the elevation? So WS2 will be WSE1 plus whatever this change is there, right? So it will be how much? WSE1 was how much? 103.2. That is 103.2 plus 0.058 meter. That is around 103.258 meters. Okay, so answer is 103.258 meters. Is it clear? So the correct answer is B, that is 103.258 meter. Okay, okay, fine. We'll move to the next question then. Okay, so the next question is which one, or let's say R, of sure sign of karst terrain. So we know that for karst terrains there will be an open water table where there will be some caves kind of things and sinkholes and all. So the correct answer for this will be all of the above. Okay, now moving on to, let's say, aquifers and all. Okay, so we know what is aquifer, right? Aquifer is a, let's say, underground layer. We have seen aquifer, we have discussed about aquifer last in the last session also, I guess. Okay, still I'll maybe write a small. So if you see different books and different literatures, you will see there are various kind of definitions that you will get for aquifer. So what is aquifer? Aquifer, you can consider one underground layer in which there will be water, or let's say aquifer is an underground layer of water bearing permeable rock, or let's say rock fractures, or let's say unconsolidated materials. Okay, so maybe the most approachable or understandable definition is an aquifer is a body of porous rock or sediment saturated with groundwater. Okay, so here now this aquifer can be classified in different forms. Maybe I'll write it in some other. Okay, so maybe if we talk about types of aquifers. So aquifers can be classified in based on several aspects. It can be classified based on, let's say, type of porosity, or it can be maybe it can be based on the rock type. Okay, so these are based on the geological origin. Okay, here we will talk about the types of aquifers based on, let's say, the presence or absence of a water table. Okay, so based on the presence or absence of water table, we can divide or classify the aquifers in three forms. First one is unconfined aquifer. Sorry, second one is confined aquifer. Third one is leaky aquifer, or let's say semi-confined aquifer. Okay, so and we'll also see perched water table. So if you just see the last figure here, if you see properly, here you can see that we have a schematic which illustrates the confined and unconfined aquifer both. Here you can see we have confined aquifer, right? And we also have unconfined aquifer. Okay, so what does this means? What is the meaning of this unconfined aquifer, or let's say confined aquifer? Generally, you will see that we call the unconfined aquifer as water table aquifer also sometimes. Okay, and confined aquifer, you will see somewhere, you will also see it is also called as artesian aquifer. We'll come to that. But before that, what is unconfined aquifer? Unconfined aquifer is the one in which a water table varies, let's say in undulating form, or let's say in slope, depending on wherever there is areas of recharge or discharge, pumpage from wells, or permeability. Okay, so if you see this water table, you see here, let's say if this is the water table, what is the pressure here? The pressure will be the atmospheric pressure. Okay, so we know that if in any aquifer the atmospheric pressure is there, atmospheric pressure. Okay, if atmospheric pressure is there and it receives water directly from the surface, then we call that as unconfined aquifer. Okay, so here you see why we are saying unconfined, because above this, whatever layer is there, from there water can permeate, okay, or infiltrate or percolate, let's say. So that's why the main thing is that the pressure above or on the water table is always atmospheric, and below that there is a impermeable strata. This one is a impermeable strata. Okay, whereas confined aquifer is an aquifer which is, and the name comes from confined. Okay, so above this aquifer and below this aquifer we have impermeable strata. So the confined aquifer is trapped between two layers of impermeable rocks. Okay, and because this aquifer is trapped between two layers of, let's say, impermeable rocks, it creates a pressure inside it, and hence the in confined aquifer there can be some pressure. Okay, so confined aquifer we also call it as pressure aquifer. Okay, it occurs where groundwater is confined under pressure greater than atmospheric pressure, and this pressure will always be more than the atmospheric pressure. Okay, so it is somewhere you will see it is also called as artesian aquifer. There is a small story behind this, why this one was called artesian aquifer. Just in 2 minutes I'll say. The word artesian is derived from the French word that is artesian, which means of or pertaining to artois. Okay, so it came from the word artois. Artois means wells. Okay, so generally it was first found in the northernmost province of France, where the first deep wells were drilled, and it was drilled to tap confined aquifers. Originally, the term referred to a well. So it is like a well. Here you can see there is a flowing well, right? So this well was first named. So the term was referred to a well with free flowing water, but presently it is being applied to any well penetrating a confined aquifer. So it was named after one well, and then later after that, all the confined aquifers are now, you can call that as artesian aquifer. So because of the pressure, if you just put one or drill one well and try to pump water, because of the pressure, what is happening? You don't have to pump water, but the water is coming itself, and that's why here you can see that there is a fountain of water, and that's why we call that as flowing well. Okay, so here from the ground surface there will be recharge also, right? So you can see a line here, a dashed line, which we call as piezometric surface. Okay, this piezometric surface, or let's say potentiometric surface of a confined aquifer, is an imaginary surface which coincides with the hydrostatic pressure level of the water in the aquifer. Okay, one more kind of aquifer that we have is perched aquifer. This we have seen in the last class also, right? That while searching for perched aquifer, maybe at shallower depth there can be a small lens kind of thing where we can have some amount of water, right? So that we call as perched aquifer here. Okay, I think that will be enough for next questions. Yeah, and yeah, we also talked about leaky aquifer, right? So, what is leaky aquifer or semi-confined aquifer? An aquifer which is overlain or underlain by an aquitard. So, we'll come to that aquitard or what is aquitards and all. But before that, maybe the question before, right? This is done. Okay, so the next question that we have is an aquifer which possesses identical hydrological properties everywhere are called. Any guesses for this? C. Okay. Yes. Okay. Yeah. So what is the question here? An aquifer which has identical hydrological properties everywhere. So if some property, not only hydrological, if any properties we consider, we see identical properties everywhere in a 2D plane, we call that as homogeneous layer, right? So for now, we can call this aquifer as an homogeneous aquifer. However, let's say if you talk about idealized aquifer, so mostly we consider idealized aquifer for our theoretical work or theoretical analysis. So what is idealized aquifer? It is an aquifer which is homogeneous, and we know what is homogeneous, which has identical properties everywhere. In case of this, we have identical hydrological properties everywhere. And isotropic. What is isotropic? Anyone? What is the isotropic aquifer? Or let's say, what is the isotropic if you just go by word also? Isotropic layer is in which if you go to all the three directions, in that the property will not change. Okay, so that is isotropic. Okay, so that if one aquifer we consider as homogeneous and isotropic, we can call that aquifer as an idealized aquifer. Okay. Okay, so the next question is, which of the following is an aquitard? Okay, maybe before that, maybe we'll see what is aquifer, aquitard, and so on. Okay, so we have now we know one of the saturated formation, right? The main saturated formation that we have talked about is aquifer, right? What is aquifer? Again, aquifer is defined as the saturated permeable geological unit that can transmit or yield some significant quantities of water under ordinary hydraulic gradients, right? So what is aquifer again? As I said, that let's say which can contain some water, in which you can yield water. This means you can extract water, or it can also store water. Okay, so water can permeate through that layer. We call that as aquifer. Okay, so whatever we will talk now is the saturated formation, which can be classified into four categories. Okay. Okay, so the next one which we have, so let's say if you give example of aquifers and all, mostly most of the aquifers you will see are unconsolidated sands and gravels, right? Because if you consolidate, the permeability will get low. Okay, the water won't be able to pass through the voids because the voids will be less for a consolidated soil, right? Okay, then other than that, we have permeable sedimentary rocks such as, let's say, sandstones, limestones. Okay, then other heavily fractured volcanic or crystalline rocks are also there. Okay, so the next one which we have is aquiclude. Okay, what is aquiclude? Aquiclude is a saturated but relatively impermeable material. Okay, so let's say if you have a material in which it is, if I write in maybe few words, it will be, although porous, sorry, but it can absorb water. Because it is porous, it can absorb water but impermeable. Okay, so just now I said, let's say if you don't consider unconsolidated sands or gravel, but you consider some consolidated one. Okay, so in that pores can be there, right? However, it so if some let's say some clay or something will be there, in that water can be on the surface of that clay. However, because it is consolidated, what will happen? The water won't be able to permeate through the voids or the interstices, right? So that we call as aquiclude. Okay, so perfect example for this will be clay, then shale, or let's say dense crystalline rock, and so on. Okay, next we have is aquitard. What is aquitard? Aquitard is again a saturated formation. However, it will have poorly permeable stratum. Okay, so it is almost permeability is almost zero. I mean negligible, and so that's why groundwater movement will not be there and does not yield free water to wells. Okay, so the examples will be sandy clay. So most of the part is sand, but some part of is clay. Okay. So in AccuTard, what will happen? It will have low permeability. Okay, that can store water. However, it can transmit water, but very slowly. Okay. And next kind of saturated formation is aquifuse. From the word also you can say that if there is no permeability, or let's say absolutely impermeable geological formation, and so that is neither porous nor permeable, we call that formation as aquifuse. For example, it can be granite or basalt rock, or it can be any compact rock also. Okay, okay. So with this, maybe we'll go to the question. Yeah. So which of the following is an aquitard? Can you give me answer for this? Any guesses? Option D. Okay. Anyone else? So the correct answer is B. So we talked about that right now, right? So solid granite, you see, it is neither porous nor it allows water to permeate through it. Okay, so that is solid granite. So solid granite will be aquifuse. Okay, clays we know that it is permeability is very low. However, it can still store water. Store water, right? So this one will be aquiclude, and aquitard is B, that is silts. And first one we know that water can be stored easily and it can be yielded easily. So it is mostly aquifer, right? Okay, so if we just see the whole picture, you see the sand and gravel is an aquifer. The silts is aquitard because it has low permeability material which could transmit water under vertical gradients only. Okay. Third is clay, that is aquiclude, that is impermeable materials is there. However, it cannot transmit water. And the solid granite is impermeable material as well as it cannot contain water also. Okay. Is this clear? Can I mean, any question is there? Okay, if not, we'll move to the next question then. Okay, so the next question, no, okay. So the next question is, most of the water coming out of continental hot springs is, your options are meteoric water, magmatic water, seawater, or metamorphic water. Anyone? Yeah, this we have seen, I mean, in the last class also, I think. So the correct answer is meteoric water. Okay. 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 So before going to this, maybe, yeah. So now we are done with, let's say, aquifer types of aquifers and all. We'll move to one of the processes which we have seen in the hydrological cycle. That is infiltration and let's say percolation. So there is a small difference between infiltration and percolation. Mostly the infiltration will be till shallow depth from the ground surface, whereas percolation will be deep. Okay, let's say after the water table. So what is percolation? Percolation is the movement of water through the soil itself. As the water percolates into the deeper layers of the soil, it reaches groundwater. Okay, and infiltration, why the process that is infiltration is important? Because let's say if you start from the ground surface, the first water that will flow, that process we call as infiltration process. So infiltration process can be used to measure the speed of water entering into the soil in case of, let's say, because let's say if dry soil is there and if some rainfall happens, then what will happen? Firstly, most of the some of the water will infiltrate. So that process we have to know to understand the later part, let's say percolation or change in storage or how water is in the aquifer after the flow and so on. Right. So mostly we will measure the infiltration using infiltrometers. You will have single ring infiltrometer, double ring infiltrometer, and so on. And or you can estimate also. Sometimes you can estimate if you have any rainfall simulator and so on. Okay. Now let's understand the infiltration rate. What is the infiltration rate? So infiltration rate is nothing but the speed at which the water can infiltrate through the soil. Okay. Now let's say we consider infiltration rate as F. Okay. And maybe so there infiltration rate. And this any of the soil, let's say if you consider clay or let's say sandy clay or something like that, it will have one infiltration capacity. So above that, the water cannot infiltrate. So let's say if there is one layer, you are putting water above it, and then water is infiltrating through that. Now, if the layer is fully saturated, the water cannot infiltrate through that layer. So in that case, the capacity that that layer will have, we call that as infiltration capacity. Okay, so infiltration rate will consider the input rate of water, or let's say rainfall intensity and the duration. Okay, okay. So I will come to this, but just to note that Horton's has given one equation, or Horton's equation, you can see, using which you can calculate the infiltration rate at any time t, and it is given as infiltration capacity plus initial infiltration minus infiltration capacity into e to the power minus k into t. So t is the time for which the infiltration occurs and k is a constant. This k will depend on vegetation and soil, what kind of soil is there, how dense it is, and so on. Okay, so now let's say if vegetation is there, then what will happen? More of the water will be infiltrated, whereas more of the water will be infiltrated, and hence the K value will be less. Whereas if let's say if there is some bare soil or something, in that what will happen? Infiltration will be less, and hence the K value will be larger. Okay. Okay. So with this, maybe we will move to the next question. Okay, so your question is if the rainfall intensity is less than the infiltration capacity, then the infiltration rate equals. Anyone wants to give answer for this? So let's consider that the rainfall intensity as I, okay, and infiltration capacity as FC, okay, and let's say the infiltration rate we call it F. What we are saying in the question, that if the rainfall intensity is less than the infiltration capacity, then the infiltration rate will be equal to what? Anyone? Yeah, Dhani, you can ask. You can switch on your audio or you can write in the. You didn't understand? You didn't understand the question or you didn't understand this part? This part. I don't know how. The equation. Okay. The Horton's equation you are saying? Yes. Okay. Horton's equation will come in the next question. Okay, I'll explain. First, let us understand this. We'll come to the Horton's equation. Don't worry. This question does not need Horton's equation here. It is a simple question. It says that let's say some rain is happening, some rainfall is happening. It has some rainfall intensity. What is rainfall intensity again? Rainfall intensity is the speed at which rainfall is occurring. Okay, so it will be in some speed unit. Okay, and infiltration capacity is the maximum amount of infiltration rate that can happen. Okay, so if the rainfall intensity is less than the infiltration capacity, then what will happen? You just think that let's say rain is happening, okay, and it is less than the infiltration capacity. So the maximum that rate at which the infiltration can happen, the rainfall intensity is less than that. Then what will happen? How much will be the infiltration rate? Maximum rate the infiltration can happen is infiltration capacity, right? And we are providing some water into it. What will happen? So, okay, let's consider some system. Okay, now we know the maximum rate or maximum infiltration rate, which we are calling here as filtration capacity, right? Now we know at what maximum speed you can move or travel through this layer. Okay, now the rainfall intensity is I, let's say, and we have I less than FC. Okay, then what will be the infiltration rate into it? Let us consider it as, let's say, you are the rainfall here, okay, and you are traveling with bike. You know your maximum capacity is 100 kilometer per hour, okay, and you can travel at any rate into that. But here, at what rate you are traveling? You are traveling at a rate of rainfall intensity. For example, the rainfall intensity is, let's say, 40 kilometer per hour. I mean, I'm just explaining to understand. Okay, so you are traveling at a speed of, let's say, 40 kilometer per hour, and the maximum you can reach is 100 kilometer per hour in that road. Okay, so now if the speed that you have, let's say 40, is less than 100, then what rate you are traveling? You are traveling at the rate of rainfall intensity here, right? So that's why if the rainfall intensity is less than that of the infiltration capacity, then the infiltration rate will be equal to the rainfall intensity. I hope you understood. Okay, Anamika, did you understand? Okay, and okay, now let's me give some other scenario, one more scenario. Okay, case 2, let's say. If the infiltration capacity, or sorry, if the rainfall intensity is greater than that of the infiltration capacity, then what do you think, what will be the infiltration rate? Now I'm saying that rainfall intensity is very high as in higher than that of infiltration capacity. Then what will be the infiltration rate? No, I mean, okay, for this question, we understand that for this question, the correct answer is rainfall intensity, that is B. I'm giving one other question, question 2, let's say. Okay, in this question, what I'm saying is rainfall intensity is greater than that of the infiltration capacity. So rainfall is happening at a very high intensity, higher than that of the capacity or infiltration capacity that the soil layer has. Then what will be the infiltration rate? Yeah, so the infiltration rate will be equal to infiltration capacity because that is the maximum infiltration rate that that layer can have. So the correct answer for that will be infiltration capacity. Okay, I hope that is clear. Okay, Okay, so we'll move to the equation first. Yeah, so in this Horton's equation, what we are after? We are after this, that is the infiltration rate. Okay, infiltration rate T here we are saying for any time T. Okay, so this equation was given by Horton using some data. So what they did is they used data for one place, and then they use the data, and then they just fit one curve into it, and then they found this, where they are considering that there was one exponential decay. An exponential decay is with one constant k, and this one is the initial infiltration rate. Okay, initial infiltration rate, let's say at time t0. Okay, if there is no rain and there is no infiltration, I mean infiltration will be there every time if it is, like say, semi-humid or semi-arid. But let's say if the soil is fully dry and there is no water to infiltrate, then the at the beginning the infiltration rate will be zero, right? And this FC, as I said, is the infiltration capacity, and from that analysis they found this equation where the infiltration rate can be equal to the infiltration capacity plus some term which is exponentially decaying. Okay, so let's say if we want to plot this, how will it be? Let's say infiltration rate on the y-axis and t on the x-axis. Then we see at time t equals to 0, what will happen? You can put in the equation and tell me. What will be the infiltration rate, Ft? If time t is equals to 0, then Ft will be equals to e to the power term will be e to the power 0. E to the power 0 is how much? 1, right? So the equation will become Ft equals Fc plus F naught minus Fc. So the infiltration rate at time t equals to 0 will nothing but F0. That is the initial infiltration rate. So let's say we are considering here we have F0. Okay, so it will start from somewhere here, and as time move, it will be exponentially decaying, and then it will again reach one value. So this one will be somewhere. This one will be the infiltration capacity, Fc. Okay, is this equation clear with this curve? And the decay constant, yeah, and the decay constant will be K. Okay, fine. We'll move to the next question then. The next question is, okay, I wanted this you to think about this, but now anyway I explain. So the question is, which of the following best describes the shape of the soil infiltration rate curve over time? Just now I have shown this. What will be the answer for this? B, correct. Just now we saw that because of the exponential term, there is a rapid exponential decrease that flattens out at infiltration capacity. Okay, so the correct answer is B. Okay, maybe this is the last question. Okay, so in infiltration and percolation, the last topic that we touched upon was the seepage, right? We talked about seepage also. What is seepage? Seepage is like infiltration, downward and lateral movement of water into the soil or substrata from a let's say, a source of supply, such as, let's say, a reservoir or irrigation canal. Okay, so this seepage water can again reappear after some time, let's say whatever topographic contours are there or water table are there because of that. Okay, so what are the factors that can affect seepage loss? Maybe you have seen that, so maybe we'll directly run to the question. Here the question is, which of the factor does not affect the seepage loss from the reservoir or canal? Any answer for this? See, metric perimeter. Okay, okay. just to understand, let's say first start with soil permeability. What is permeability? Permeability is characteristic or the property of the soil through which it allows any liquid to move through it, right? So if a soil has less permeability, this means what? That the water will be, the water or whatever movement of water is there, it will be less, right? If the soil has more permeability, this means more water can flow through the voids or interconnected voids, right? So here we are talking about seepage, which is again infiltration, let's say downward, along with lateral movement of water. So it depends on the soil permeability, because if low permeability is there, seepage loss will be less. Whereas if there is high permeability, more water can flow and hence seepage loss will be higher. Okay. Third one which we are talking about is wetted perimeter. Here I am talking about a reservoir or canal, right? So let's say if one canal is there, which is somewhere trapezoidal, let's say. What is wetted perimeter? So let's say water is flowing somewhere near this. Okay. Wetted perimeter is the perimeter which is getting wet because of this water. Okay, so now you see that if the wetted perimeter is more, this means it will go up, right? So the seepage loss will be less, otherwise it will seep into the layers, right? So it will also depend on wetted perimeter. If not, next one is silt deposition. If on over the time the silt is getting deposited, because of this silt, water won't be able to flow through the flow downward, right? And that's how seepage loss again will change. So the factor which does not affect the seepage loss will be prevailing wind velocity. Mostly this wind velocity will affect the evaporation that is happening. So let's say if some water is getting evaporated from the open surface, if there is wind velocity, because of this velocity, what will happen? The evaporation will get affected. The seepage loss won't be. So the correct answer would be B, that is prevailing wind velocity. Okay, I think that's it. Yeah. So, so with that, we will end today's session. If you have any questions or any doubts, you can ask me. Any questions or any clarity if you want to in today's session or in the week 2 lectures, you can ask me. If not, we can close the session now. No doubt, no? Okay. Yeah, if you guys have any doubt anytime, you can put in the Q&A section of the uh, NPTEL that form. Okay. Okay. So with that, we'll end our session today. Thank you so much. We'll meet again next Monday, 6 to 8 for week 3 lectures session. Okay. Thank you so much. Thank you, sir.